We begin with the heart of the matter. Your computer is a general-purpose machine. That's a term we throw around, but what does it really mean? It means it wasn't designed to do just one thing. A pocket calculator is a special-purpose machine. It only does math. A digital watch is a special-purpose machine. It only tells time. But your computer, it's a writer, an artist's canvas, a movie theater, a recording studio, a global communication hub, and a gateway to infinite information. Its power comes from its ability to connect with an incredible variety of input and output devices. We call them peripherals. Your keyboard and mouse are inputs. Your monitor and speakers are outputs. Your hard drive, printer, and webcam are all part of this sprawling, diverse ecosystem. The computer is like a master conductor, and all these devices are the orchestra. But this raises the central question, the one that forms the foundation of our entire journey today. How does the conductor, the CPU, actually talk to every single musician in the orchestra, especially when they all play different instruments at wildly different speeds? The first, most intuitive guess is that the CPU, being the brain, must directly control everything. It must be telling the printer head exactly when to spray a dot of ink, listening for the exact moment you press the G key, and telling the hard drive's platter exactly where to find a file. It sounds plausible, right? The boss gives the orders. But let's think about that for a second. Your CPU is a marvel of engineering, a sliver of silicon that operates at gigahertz speeds, meaning it can perform billions of actions every single second. It lives in the nanosecond world. Now, consider a peripheral like an old-school mechanical printer. To print a single character, a physical print head has to move across a page, a ribbon has to strike, and the paper has to advance. These are mechanical actions that take milliseconds, a thousandth of a second. To your CPU, a millisecond is an eternity. It's like asking a Formula One driver to get out of their car at every turn to personally inspect the tire pressure before continuing. Well, the CPU is waiting for that slow, clunky printer to finish its mechanical dance. It could have performed millions, if not billions, of other calculations. It would be sitting there, twiddling its digital thumbs, completely wasting its incredible power. The same goes for you, the user. You might think you type fast, but to a CPU, your typing speed is glacial. The time between one keystroke and the next is a vast, empty desert of inactivity. If the CPU had to personally monitor the keyboard, waiting for your next press, your computer would grind to a halt. The entire system would run at the speed of its slowest component. It would be like an entire factory shutting down because one worker is slowly, carefully painting a single screw. This is not just inefficient, it's a recipe for a useless machine. The brilliant minds who designed the first computers quickly realized the CEO shouldn't be running the mailroom. The brain shouldn't be micromanaging the body's every little twitch. There had to be a better way. To really feel this inefficiency in our bones, let's zoom in on a classic example, the keyboard matrix. Your keyboard isn't just a simple collection of buttons. Underneath those keys lies a grid, a matrix of wires arranged in rows and columns. When you press a key, you connect a specific row wire to a specific column wire, closing a circuit at a unique intersection. In the early days, the computer had to figure out which key you pressed by itself. How did it do this? Through a mind-numbingly tedious process called scanning. The CPU would send a small electrical signal down the first row and then rapidly check every single column to see if a connection was made. If it found nothing, it would move to the second row and check all the columns again, then the third row, and so on, over and over, hundreds or thousands of times a second, in a constant, repetitive loop. Is row 1 connected to column 1? No. Is row 1 connected to column 2? No. Is row 2 connected to column 1? No. This scanning loop consumed precious CPU cycles. The entire processing power of the computer's brain was being held hostage by the monotonous task of asking, is a key pressed yet? How about now? Now. This is the very definition of micromanagement and the perfect illustration of the problem. It became painfully obvious that these low-level, repetitive hardware chores needed to be offloaded. The CPU had more important things to think about, like running your programs. The system needed middle managers, and so, the era of the device controller was born. This was the revolutionary idea that solved the micromanagement problem. Instead of the CPU talking directly to the raw mechanics of a hard drive or the wire grid of a keyboard, it would talk to a specialized, dedicated chip built right into the peripheral itself. These onboard microcontrollers are, in essence, tiny, special-purpose computers. A modern keyboard doesn't just have a matrix, it has its own little brain. This controller's only job in life is to watch that matrix. It performs the tedious scanning loop, and when it detects a key press, it figures out which key it was and only then reports the result to the main CPU. The hard drive has a powerful controller that translates a simple command like "get me this file" into the complex sequence of moving actuator arms, spinning platters, and locating data sectors. Your graphics card is the ultimate example. It's essentially a supercomputer in its own right, with its own processor, the GPU, and memory dedicated entirely to the task of drawing what you see on the screen. These controllers act as brilliant interpreters and supervisors. The CPU, now acting like a true CEO, can simply issue high-level commands. It doesn't say, "Move the print head to millimeters to the right, fire nozzle 7, now move another 2 millimeters." Instead, it sends a block of data to the printer's controller and says, "Print this." The controller handles all the messy, slow, mechanical details. The CPU sends a command to the hard drive controller saying, "Save this document." The controller takes over from there. This frees up the CPU to focus on the big picture. It communicates with its peripherals through a shared connection pathway called a bus, but it's no longer a conversation of control. It's a conversation of commands and results. It's delegation, the most powerful principle in all of computing and, frankly, in all of management. Okay, so the CPU talks to these controllers, not the raw hardware. But how does that conversation actually happen? How do you send a command from the CPU to a controller for, say, the network card? Over the decades, two main models have emerged for this hardware communication. First, there's memory-mapped I/O (MMIO). This is arguably the most elegant and common method used today, especially in the ARM processors that power your smartphone. Imagine all of your computer's memory RAM as a giant street of numbered mailboxes. The CPU is used to reading from and writing to these mailboxes. That's how it runs programs. With MMIO, a certain range of these mailbox addresses aren't connected to actual RAM chips. Instead, they're wired directly to a device controller. So when the CPU writes a value to memory address OXDEADBEEF, it might think it's just storing a number. But in reality, that address is a special mailbox for the graphics card. Writing to it might be a command that tells the card to change the screen resolution. Reading from another special address might give the CPU a status update, like "I'm finished drawing the last frame." To the CPU, it all looks like memory. It doesn't need to learn a new language or use special instructions. It's just reading and writing to its familiar street of mailboxes, but some of those mailboxes are portals to other devices. It's a simple, unified, and powerful abstraction. The second method is called isolated I/O, or sometimes port-mapped I/O. This is the model historically used by x86 processors from Intel and AMD, the kind you'd find in most desktops and laptops. In this model, devices don't live in the same address space as memory. Instead, they have their own, separate phone book with a set of port numbers. To talk to a device, the CPU has to use special, dedicated instructions, like in and out. It's like having a private phone line just for talking to peripherals. So instead of a simple move instruction to a memory address, the CPU would have to execute a special out instruction to a specific port number. The trade-off, it keeps the memory map clean and simple. There is no chance of a buggy program accidentally writing to a device register and causing chaos. but it also means the CPU needs a more complex set of instructions. Over time, while x86 systems still have this legacy capability, most modern devices within them have moved to using memory mapped for its flexibility and simplicity. So we've established that the CPU can send commands to devices by writing to their mailboxes, but communication is a two-way street. How does the device let the CPU know when it's finished with a task? Or how does a keyboard let the CPU know that a key has just been pressed? Again, there are two primary methods. The first is called polling. This is the digital equivalent of a kid in the backseat of a car asking, "Are we there yet? Are we there yet? Are we there yet?" In a polling system, the CPU is responsible for constantly checking in with the device. It will repeatedly read a status register, one of those special mailboxes from the device controller, looking for a change. For example, it might keep asking the printer, "Are you done with that page yet?" The status bit will be 0 busy until the page is finished, at which point it flips to 1 ready. You can immediately see the inefficiency here. The CPU is once again caught in a loop, wasting its time checking a status that might not change for a very long time. It's better than micromanaging the hardware directly, but it's still far from ideal. This brings us to the second, and far more brilliant, method, interrupt-driven I/O. This is the dominant model in every modern computer. Instead of the CPU constantly nagging the device tells the CPU when it needs attention. It is like a polite passenger who simply taps the driver on the shoulder when they need to say something, rather than shouting from the backseat every 5 seconds. Every CPU has a special wire called an interrupt request line. When a device, like a keyboard controller, detects a key press, it sends a small electrical signal down this line to the CPU. This signal literally interrupts the CPU from whatever it was doing. The CPU immediately pauses its current task, saves its place, and jumps to a special piece of code called an interrupt service routine ISR. This routine is the handler for the interrupt. It figures out which device sent the signal, reads the keystroke data from the keyboard controller's mailbox, processes it, and then tells the CPU it can go back to what it was doing before. Interrupts are the cornerstone of modern multitasking. They allow the CPU to be working on a complex calculation for your spreadsheet, and the very instant you move your mouse, the mouse controller can interrupt. The CPU can quickly process the cursor movement and then seamlessly return to the spreadsheet, giving you the illusion that it's doing everything at once. It's not constantly checking on the mouse, it's being notified by the mouse. It's a beautifully efficient, event-driven system, so let's put it all together. Contemporary computers use a powerful and elegant combination of these two ideas. They primarily use memory mapped for the CPU to send commands and data to device controllers, and they use interrupt-driven I/O for the devices to signal back to the CPU when they need attention. When you want to download a file, your operating system, under the direction of the CPU, uses memory-mapped registers to tell the network card as controller where to find the data in RAM and where to send it on the internet. The CPU then moves on to other tasks, updating your clock, rendering a video, whatever. It doesn't pull the network card. Milliseconds or even seconds later, when the download is complete, the network controller sends an interrupt. The CPU pauses, runs the service routine that marks the download as complete, and then resumes its work. It's the best of both worlds, a simple, unified way to address devices and a highly efficient, event-driven way to receive notifications from them. Now, I have to confess I've been using a helpful simplification. I've been saying that these device mailboxes are just like memory. Well, that's how the CPU sees them. The reality under the hood is a bit more complex. Devices don't actually behave like RAM internally. RAM is simple. You give it an address and a value, and it stores it. Devices are complex state machines. Writing to one register might trigger a whole cascade of actions. In reality, there's a crucial layer of translation happening. In older computer architectures, this was the job of a dedicated chip on the motherboard called the North Bridge. The North Bridge was the master traffic controller. It sat between the CPU, the RAM, and the high-speed peripherals. When the CPU tried to write to a memory address that belonged to the graphics card, the North Bridge would intercept that request. It would recognize that this wasn't a request for RAM and would translate the CPU's simple memory-style communication into the more complex command protocol required by the dedicated bus the graphics card was on, like a GP or, later, PCI Express. It was the wizard behind the curtain, making the illusion of memory-mapped I/O possible. This brings us to the fascinating history of the motherboard itself. For a long time, PCs were designed around a two-chip system, the North Bridge and the South Bridge. The North Bridge, as we said, was the high-speed hub connecting the CPU to RAM and the graphics card the system's freeway. The South Bridge was a slower hub that connected to all the other, less demanding peripherals, the hard drive, USB ports, keyboard, and audio the system's local roads. The CPU talked to the North Bridge, and the North Bridge talked to the South Bridge. But as CPUs and peripherals got faster and faster, this architecture started to create bottlenecks. The connection between the CPU and the North Bridge, known as the frontside bus, became a major traffic jam. The solution: evolution through integration. Engineers decided to move the North Bridge's most critical functions directly onto the CPU die itself. First, the memory controller was moved into the CPU. This gave the CPU a direct, private superhighway to the system RAM, dramatically cutting down on latency. Then, controllers for the fastest buses, like PCI Express for graphics cards, were also integrated. What was left of the North Bridge and all of the South Bridge as functions were eventually consolidated into a single, smaller chip, known today as the Platform Controller Hub PCH, or simply the chipset. If you look at a modern motherboard, you'll see the CPU socket and one other major chip. That's the chipset. The CPU now has direct lanes to the most important components, and it talks to the chipset to handle everything else. This evolution was all in the service of speed, eliminating the traffic jams of the past and allowing every component to communicate more efficiently. With all this complex talk of integrated controllers and dedicated buses like PCI Express, you might be wondering, why do we still bother with the illusion of memory-mapped I/O at all? Why not just have the CPU speak the native language of these modern buses directly? To answer that, we have to take a trip back to the 1970s and 80s, the Wild West of personal computing. In that era, every computer brand was its own isolated island. An Apple II, a Commodore 64, and an IBM PC might all use a similar CPU, but the way they wired up their keyboards, disk drives, and video outputs was completely different and proprietary. Each one had its own hardwired, unique memory map for its I/O devices. This created total incompatibility. A printer card designed for an Apple II was a useless piece of plastic to an IBM PC owner. This fragmentation was a massive barrier to progress. The solution was to create a standardized abstraction. By agreeing to use universal I/O buses like the ISA bus, then PCI, and now PCI Express, and by presenting these buses to the CPU through the standardized lens of a memory-mapped address space, the industry created a stable platform. Hardware manufacturers could now build a single graphics card or network card that would work in any machine that supported the PCI Express standard. The memory-mapped I/O model, managed by the chipset and operating system, provides a consistent front door for the CPU to knock on, regardless of the intricate and varied plumbing that lies behind it. It's the great peacemaker that allows a Dell monitor, a Logitech mouse, and a Samsung SSD to all work together harmoniously inside a computer with an ASUS motherboard. We've now standardized the physical transportation of data with buses like PCI, USB, and SATA. They're like the world's standardized shipping containers. A USB port can carry data for a keyboard, a mouse, a printer, or a webcam. It doesn't care about the contents, only the container. But there's one final, crucial piece of the puzzle. Even if you have a standard plug and a standard bus, the language spoken by a specific HP printer is different from the language of a Canon printer. Each device is unique. How does your operating system, like Windows or Mac OS, know how to translate its generic print command into the specific, hardware-level instructions that your particular printer understands? The answer is the device driver. A driver is a small, highly specialized piece of software that acts as the final translator. It is written by the hardware manufacturer, for example, NVIDIA, HP, Logitech, and it effectively teaches the operating system how to speak the unique language of that one specific piece of hardware. When you install a new graphics card, you install its driver. That driver tells Windows exactly which memory-mapped mailboxes to use to control the card and what specific values to write into them to achieve effects like changing the resolution or rendering a 3D object. The driver completes the chain of communication, bridging the final gap between high-level software commands and the low-level electrical signals of the hardware. It's the unsung hero that makes our plug-and-play world possible. So after this deep dive into the hidden conversations happening inside our machines, what have we learned? I believe there are 3 overarching takeaways that are not only fundamental to computing, but are also profound lessons for our own lives. First, CPUs communicate with devices. They don't control them directly. The heart of modern efficiency is delegation. A smart system, whether it's a computer or a company, empowers specialized units to handle their own tasks and trusts them to report back only when necessary. Micromanagement is death to productivity. Second, modern systems are a beautiful blend of abstraction and reality. We use the simple, elegant abstraction of memory-mapped I/O to make the software developer's life easier, while under the hood, a complex reality of dedicated buses and translation logic ensures everything runs at maximum speed. It teaches us the power of creating simple interfaces for complex systems. And third, standardization is the silent engine of innovation. It was only when the industry agreed on common buses, common connectors, and common communication models that the explosive ecosystem of universal peripherals became possible. Cooperation on a foundational level allows for infinite creativity and competition on top. Thank you so much for joining me on this deep dive today. I hope this has demystified the inner world of your computer. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.